Welcome to the Launchpad, everyone. Imagine for a second you're sitting at the control console of a multi-billion-dollar space mission. The countdown is ticking, the engines are primed. In this scenario, there is absolutely zero margin for error. Every single calculation, every tiny parameter must be perfect for launch, or the whole thing literally blows up in your face. Well, today we are tackling the computer science equivalent of that zero-margin space mission. We're diving into what is, without a doubt, one of the most notoriously misunderstood areas across the entire Cambridge syllabus. Whether you're sitting the 9618 A-level or building your foundations in 0417, 0478, 0983, 0984, or 2210, I am talking about the assembly language instruction set, specifically mastering MOV, STO, ADD, and sub. If you've ever looked at assembly code and felt like you were staring at an alien language, you are absolutely not alone. It trips up thousands of students every single year. Let me tell you about two typical students we see all the time. First, we have Alex. Alex is the kind of student who overloads their answers with raw computer science facts, memorizing every single definition in the textbook, but completely forgetting to analyze the actual problem. And then we have Sam. Sam rushes. Sam looks at the command word, panics, misses the core requirements, and just starts writing code, hoping something sticks. Both of them lose massive marks, and today we're going to fix that. We're going to look directly at the data, decode the examiner reports, and turn this weakness into your absolute greatest strength.
Here is our flight plan for today's mission. We're covering, number 1, the assembly language challenge. Number 2, core cognitive domains. Number 3, the technical methodology. Number 4, critical examiner insights. And number 5, securing your method marks. Let's get right into it.
Section 1, the assembly language challenge, validating the struggle and understanding the stakes. So, I want to pose this critical question directly to you right now. Think about it. Why do students find multi-step calculations and method marks so incredibly hard when it comes to assembly commands like MOV, STO, ADD, and sub? Well, digging into the source material reveals the hard truth. Assembly language strips away all the cozy, comfortable safety nets of high-level programming like Python or Java. You don't have built-in functions catching your typos. You are working right next to the bare metal of the hardware. You aren't just writing a program, you are manipulating raw data at its most foundational, granular level. When your exam calculations require multiple steps, like moving data into the accumulator, adding a secondary value, checking for an overflow, and then storing it back into a specific memory address, your cognitive load absolutely spikes. It's like juggling flaming torches while trying to solve a Rubik's Cube. It is incredibly easy to lose track of your logic midway through. Think back to Sam, who rushes through exams. When Sam sees a multi-step calculation, the instinct is to jump straight to the final binary answer. But in assembly, skipping steps is fatal. One wrong register movement, one misaligned address, and your entire program crashes. The margin for error is literally zero. You need a systematic, foolproof way to handle this complexity without burning out your brain. Section 2, Core Cognitive Domains, Decoding the Assessment Framework. Now, before we look at the exact framework you need, I have an important reminder. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's talk about how the examiners actually grade you. They aren't just checking if you've memorized what the letters MOV stand for. The Cambridge assessment benchmarks require logical, structured reasoning that targets very distinct cognitive domains. We're talking about knowledge and understanding, application, and analysis. The exam framework deliberately prioritizes analytical depth over superficial breadth. This is exactly where our other student, Alex, completely falls apart. Alex will write down a perfect dictionary definition of the accumulator and the arithmetic logic unit, but the examiner doesn't care about a dictionary definition if you can't apply it. They want to see exactly how deep your understanding goes when you are actively manipulating these registers under pressure. They are testing your reasoning, your logic, and your ability to foresee the consequences of an instruction. It's not about how many facts you can recite, it's about whether you can pilot the ship. The top-performing candidates, the ones securing those elite grades, do not rely on rote memorization. Mastery requires a deeply connected conceptual understanding, systematic analysis, and evidence-based reasoning. Let me give you the golden phrase for Cambridge exams: transferable to unfamiliar contexts. You are guaranteed to face scenarios in that exam hall that you have never seen in your textbook or your class notes. That's by design. Your ability to take the fundamental principles of MOV, STO, ADD, and sub and dynamically apply them to a brand new, terrifying problem is exactly what separates an average answer from a brilliant one. To do this, you need structure.
Just like you might use the Peel framework point, evidence, explanation, link for an essay, in computer science, your code is your framework. Your command is the point, your register data is the evidence, your logic is the explanation, and your final store instruction links it all back together.
Section 3. The technical methodology. Your step-by-step processing engine.
All right, it's time to transform your approach. When you encounter a multi-step assembly language problem, you cannot just guess. You must follow a rigorous, standardized sequence. This is your success blueprint. Step 1. Deconstruct the command words in the question. Are they asking you to evaluate, trace, or write? Step 2. Extract the relevant data, which is often hiding in complex binary or hexadecimal representations. Step 3. Select your analytical framework. Step 4. Execute your analysis with crystal clear notation. And Step 5. Present it using perfect terminology. Let's make this super concrete with a live rewrite. Imagine Sam rushing through a question asking to total two values. Sam just scribbles down a random binary number. 0 marks. Now let's turn that red pen into a green check mark using our 5 steps. We don't just output an answer, we step through it. First, we extract the initial value by moving it to the accumulator. We write MOV ACC 100. We are explicitly stating our action. Then, we execute the addition, ADD 101. Finally, we secure the result by storing it properly back into memory, STO 102. Boom. Following this exact 5-step sequence brilliantly illustrates a perfect answer. It completely eliminates the panic of not knowing where to start, and it lays out an undeniable paper trail that practically forces the examiner to give you maximum marks.
But we don't just stop at answering standard questions. Your practical application develops your wider programming skills through a very specific, repeatable cycle. You start by designing your algorithm using your MOV, STO, ADD, and subcommands. Then you implement the solution. And here is the crucial part that 80% of students skip. You test thoroughly to verify your results, and you evaluate the performance. This deconstruct, solve, evaluate cycle is literally the beating heart of computer science problem solving. Imagine a 60-second timer on your screen right now. If you were speed writing a trace table for an algorithm you just implemented, you have to run through every single test case. Does it work with zeros? Does it work with negative numbers? Testing isn't an afterthought, it's the shield that protects your grades. Section 4. Critical Examiner Insights. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at aceexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @aceexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's get into the most valuable part of today's explainer. Direct feedback extracted straight from the principal examiner reports. These are the 3 critical warnings that constantly cost students their hard-earned marks. Treat this like a find the flaw challenge. Number 1, confusing cause and effect. Students constantly mix up which register is being read from and which is being written to. With a command like STO, are you pulling from the accumulator to the memory or memory to the accumulator? Getting that backward is a fatal flaw. Number 2, forgetting boundary conditions and edge cases. Say you use an add instruction. Did that addition result in an 8-bit overflow? If you don't explicitly handle or mention that overflow in your trace table, you lose the mark. The examiner reports are practically screaming about this. And number 3, answers lacking specific question context. The exam will give you a specific scenario, like a temperature sensor feeding data to a microprocessor. If your answer just generically describes what sub does without mentioning the temperature sensor, you get generic marks, which usually means 0. Your code must speak directly to the world the examiner built in the prompt. So how do we push past standard answers and reach that top-tier, elite level? It comes down to the difference between standard problem solving and evaluative thinking. Standard problem solving is great. It means solving systematically and checking if your answer seems reasonable. But evaluative thinking, that is how you dominate the exam. Evaluative thinking means you consider multiple solutions, you actively analyze the trade-offs, and you acknowledge the limitations of your code. In the context of assembly language, this translates to evaluating algorithm quality. You aren't just writing the move and add instructions, you are identifying the time complexity. You are looking at the space complexity. How many memory registers are you burning through? How do those edge cases we just talked about affect the overall performance of the system? If you can evaluate your own code and justify your technical decisions with clear, traceable evidence, the examiners will be absolutely blown away. Section 5. Securing your method marks. Your ultimate exam survival strategy. Please, if you remember absolutely nothing else from today, burn this into your memory. This is a direct, urgent alert from the examiners. Quote, students lose marks by not showing working. Even if your final answer is wrong, method marks can save you.
In assembly language, the analytical process is exactly as important as the final answer. Let's go back to our space mission analogy. If the rocket crashes, the engineers need the black box to see why it crashed. Your working out is your black box. The method mark strategy means you are rewarded for your pure logic. If you execute a brilliant 5-step process with clear notation, but you make one tiny, silly arithmetic slip on a mental math add instruction, a clear paper trail allows the examiner to follow your logic and award you almost all the credit. But if you just write down a final binary or hex value without proving how you got there, 0 marks. Never, ever drop a final answer onto the page without proving the logical steps it took to arrive there.
To help you execute smoothly under the immense ticking clock pressure of the exam room, here is a quick tactical tip. Create your own memory hack for the instruction set. Build a mnemonic for MOV, STO, ADD, CUB using the first letters of key terms that actually click with your brain. Maybe it's move safely, always subtract, or whatever vivid image helps you. Having a personalized mental cheat sheet helps you completely bypass that horrible exam day brain freeze. It acts as an anchor, instantly grounding you back into the systematic time management matrix we've discussed today. When you aren't stressing about remembering the commands, you can spend your time actually analyzing the problem. I want to leave you with this final, provocative thought. Code is not just a list of instructions for a machine, it is a logical argument presented to a human examiner. When you write out your MOV, STO, AD, and subsequences, you are essentially standing up in a courtroom and proving that you truly understand the deeply complex architecture of the computer. Are your steps clear enough to prove your logic? Treat your code like an ironclad, evidence-based argument. Show you're working to secure every single method mark, and you will absolutely master this crucial section of the syllabus. Now, listen closely. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @ACExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @ACExams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.